Hello again. My name is Frans and welcome to today's session. In our previous video or our previous session, we spoke about uh, how to solve or rather how to draw free body diagrams, and then I showed you two types. The free body diagrams of an object that is on a horizontal surface being pulled basically of this particular category, if I were to just remind you in this way, whereby an object is being pulled straight on a horizontal surface. The angle between the force applied and the horizontal, or rather the surface, will be 0 degrees. So this was the first one, the first free body diagram that we did. The second one was on the very same horizontal surface, but the force that pulled this particular object was at a particular angle that we called theta yesterday. And one of the most important things that I spoke about was to show you how to come about breaking this force component, or rather this force, into components, being the vertical component called Fy, and then the horizontal component called Fx. And I also mentioned that some books can also call this Fy to be Fv, and then this Fx as F horizontal. So whichever way they would want you to, or maybe they would present it, just know it means the same thing. So, and then another important thing that I need to remind you of is the fact that objects that on a horizontal surface, for example, this one, have what you call 4 different types of forces, which is the force applied, and then the normal force which goes up, and then the force due to gravity which goes down, and then the gravitational force, which basically only happens if the object happens to be on a rough surface. So if I were to draw the free body diagram, the one on top will be something like this: a dot, and then a force applied. I said if the object is moving, force applied will be the longest force on this particular, acting on the object, and then normal force and weight, or force due to gravity, have to be basically of the same size, or rather the same magnitude. And then force due to gravity, or rather sorry, gravity frictional force, will be shorter than the force applied. And I showed you what was the reason behind that. We remind ourselves of the vectors and scalars. So now if I were to name them, this will be our force applied, normal force, weight, and then Fk for objects that are moving. And then here I'm going to break this thing. I showed you two things. First one was the free body diagram of calculations, which basically you use this free body diagram when you do calculations. And then the one is the free body diagram that they ask you for. Normally they will say 4 marks. So I call it the free body diagram of marks. So if I were to just draw a line to separate the two, I'll just rewrite these things again and write marks and then calculations. So since the object is going up, we have our dot here. We're going to have that upward at an angle force, and then our normal force and weight being going opposite direction but the same size, and then Fk going in the backward opposite direction. So this is going to be our force applied, normal force, weight, and then Fk. So this will be, if they say to you 4 marks, you are going to give them this particular free body diagram. But if they ask you to find, or rather they say 5 marks, or maybe you, after drawing this one, the calculations that are going to come afterwards are going to be dependent on the free body diagram of calculations, which basically comprises of the components of forces, which basically we are going to have this thing, Fk, normal and weight, normal force and weight. And then I showed you this one, which is going up, since this force is pulled, or rather the object is pulled at an angle that is going up. So the Fy, our Fy is going to go upwards, and then our Fx, since the object is accelerating to your right, is going to be going to your right hand side. So this is basically, just to recap, on what we've done yesterday. So this is just a recap of what we've done yesterday. So today we are going to proceed on the very same topic, but we are adding some flesh into it, or rather showing you some other free body diagrams and the different types of them. So I want to show you again on the very same axis, which is basically the free body diagram of objects that are on a horizontal surface. But now, let's look at this particular one. And then they say to you, the force applied comes from beneath, or rather, it is done like this. This object is being pushed. Force applied will be put in that particular direction. Seems like someone is pushing something from underneath something. So he or she is pushing something upward. You see? So we have to redraw this particular structure in this particular manner. Since it is being pushed, the force applied is going up. As you can see, there is our basically horizontal surface, and then there is an angle between the horizontal and the angle, or rather the force applied. This particular structure, it is the same as the one that we've drawn, which is like this. I hope this basically will help you in a sense that you will know if they say to you something is being pushed from underneath or from the bottom, you know, oh, it's the same thing that I've done. So basically, there's no need for me to stress or maybe to cringe or behave in some way. So if they say to you this particular force is being pushed from the bottom or from beneath, you just know it's the same one that we've done yesterday, which is what we've just recapped now. So you just redraw it and put it in a manner that you basically understand and know, and afterwards you will be having a walk in the park understanding of things. I hope this basically makes sense. Now, let's have an object that has a force like this. A particular object of this nature, remember a lawnmower. A lawnmower, it has a handle here, but a mower is down there, so its handle is here. So they are pushing it downwards, as you see. So sometimes, or rather, when someone is mowing the lawn, maybe at home or maybe at school or whenever you're walking around, you'll find or rather see someone pushing something standing here while the mower is somewhere down there. So there is an angle between the surface and the handle, or maybe the force that is being applied on this particular mower. So the same is true again with the previous one that we've done, but this one is going down. So what do we need to do? Let me do my famous thing. We are going to have the free body diagram of Max, and then the free body diagram of calculations. Sorry about that. Calculations. Yes. So now let's check how are we going to draw this thing? We will have our dot here. And then I want us to draw the three first parts, which is normal force and weight. I'd like us to believe that almost everything that I'm going to draw will be on a rough surface, such that we can include the frictional force. So it's normal, weight, and then Fk. Like here, the force is being pushed downwards. So we will have force applied that is being pushed downward, even though the object is going forward, but the force applied is being pushed in the direction that is going downward. As an example that I've done of a lawnmower. Lawnmower moves forward, yet the force that is being applied on it is the force that is going down, So now, the very same thing that we've done with the previous one of what I've just recapped now. For calculations, I'm going to draw something like, I'm going to complete this particular thing and create something like a right angle triangle. Now here I'm going to have my y, fy, and then here I'm going to have my fx. So this is basically our theta is going to be there. So my force that is in the opposite direction to theta is fy. Which one? The one that is adjacent to theta is fx. So if I were to remind you of what we said yesterday, we said fx is going to be fa cos of theta, and then fy is going to be fa sine of theta. When we do some few problems after this particular illustration, I'm going to come with a question that is going to make us utilize this formulae such that we understand basically how to use them, not only see and not use. So now we have fy. Now remember one thing. In the previous question example, force applied was going up, and then our fy was going in the up direction. Now force applied is being pushed downwards. That simply means one thing. If we draw this part here, we'll have our normal force, we will have our weight, and then our fk. That simply means our fy is going to go in the downward direction because the force applied is pushed in the direction that is going downwards. And then since the object is moving to the right, even though it's being pushed downward, our force component, the horizontal component, is still going to go to the right. So this is fy, and this is weight, and this is normal force, and this one is going to be our fk. So this is what you are going to use for calculations, and this is what you are going to use for marks. So I hope this particular stuff makes sense for objects that are on horizontal surface. Horizontal surface pulled at zero angle, horizontal surface that is being pulled at an angle that is greater than zero. So the first one is pulled at a zero angle, upper angle, and then the angle going downward. Those three, very much important. You will see when we make example or rather solve some few problems. Now let's see what question can we find whereby we have to use these three free body diagrams. Question 1. Frans is pulling a box horizontally to the right with the force of 30 newtons, and there is a 15 Newton frictional force experienced by the box. Then question 1 would say, number 1.1, draw a free body diagram indicating all the forces experienced by the box. And then the max given will be 4. Second question, calculate the net force, or rather, let me just say net force. Question 3, I forgot something here, but a box of 10 kg mass. Calculate the acceleration of the box. So the structure of the box will be something of this nature. 10 kg being pulled to the right at 30 newtons force. Yes. And then we are told that Fk is equal to 15 newtons. So this is basically what our question comprises of, or rather our statement and question has. So if we're basically to dissect what this question is asking us, let's break it down. Frans is pulling, he is pulling the box horizontally to the right. We have the direction with a force of 30 newtons, which is the force applied in this case because he is pulling. And then there is a 15 newtons frictional force, meaning the 15 newton force opposing the motion of this moving object, which basically means it goes in the opposite direction of the 30 newtons. Now, the mass of this object is 10 kg. We now have the mass. What is the first question asking of us? We are asked to draw the free body diagram and indicating all the forces this box experiences. Bear in mind, they did not tell you about the normal force, they did not tell you about the weight. So, but the max, indication of the max is the one that tells you how many forces are there. So max indicates the number of forces you should show when you draw your free body diagram. Let's start with solutions. Or rather, sorry, let me continue reading the questions. The second question says, calculate the net force. You see, so you're going to have to calculate net force of the forces experienced by the box. Last question would say, calculate the acceleration of this force or other box. Let me try by answering the first question. Solution. Question 1. We check. We were told 4 marks. So now let's draw our free body diagram. Start firstly by showing your dot. It needs to be clear. And then we have a 30 Newton force applied to the right. 30 force applied. And then also, do not forget our normal force and weight. And care should be taken. As you can see, my arrow is on top, exactly on top of the line. So there is no space like this that I've created, as if like I'm just making something that I just don't want to finish. So exactly the arrow has to be on top, or rather it should be a best fit line, or line of best fit, if I were to use a mathematics jargon. So now, frictional force, remember, we have a 30 Newton force, and now we have a 15 Newton force. Obviously, it is going to be of lesser size, Fk, F normal, and then weight. Now, how many forces do we see here? 4. How many marks are we asked, are allocated for that question? 4. Then our question is answered perfectly so, without any problems. Now let me try to erase here such that I can continue answering those other two questions. So when it comes to calculation questions, I would like to advise you to firstly start by noting down what is it that you are given under the radar of writing it as data, or rather data. I don't know basically how many people, or rather how people pronounce that, but I'll go for data. So let's say question number 2, you write it as data, and then we check. We are asked to find the net force. So now remind ourselves, or rather remind yourselves of vectors and scalars. We have vertical forces, and then we have horizontal forces. So basically we will have to find the net horizontal forces and the net vertical forces. Also, remember I said normal force and weight are of equal magnitude. So if normal force and weight are of equal magnitude, that simply means their values are the same. Sorry about that. So let's start by saying force net, I'll say force net horizontal, H for horizontal, which is going to be force applied plus Fk. Cool. And then we'll say we take right as positive. Now we will be having 30 minus 15, which will therefore give us 15 newtons to the right, if we use it in a manner that will help us to also remember vectors. Remember, force is a vector quantity. That will be the first part of the question. The second part of the question, how can we find the magnitudes, or rather the values of normal force and weight? Let's start first by calculating weight, because we know the formula for weight. So the formula for weight is going to be mass multiplied by gravitational acceleration, which is g, right? And then we will end up having what? 10, which is the mass, multiplied by 9.8. And this will basically give us 98 newtons. Weight is acting downwards, so it's going to be down. Cool. However, we have to come to this particular thing. Weight is equal to normal force is equal to mg. This is basically what we mean when we say normal force is equal to weight. That is that. Now, however, if maybe we're to remember Newton's third law of motion, these two are of equal magnitude but in opposite direction. So if we have 98 here, that simply means here we will have negative 98. Cool. Now let's find force net vertical. Is going to be weight plus normal force. Now let's say down is positive just to respect gravity. We will end up having 98 minus 98, which is going to give us 0 newtons. It's a neutral force, meaning they're cancelling each other out. Now, it tells us one thing. The net force now, we have net force of horizontal forces and net force of vertical forces. I hope this one makes sense. Let's go and attempt question number 3. Cool. As you can see, I did not erase the data part, or rather the data part. So question number 3 says, calculate the acceleration of the box. Acceleration of the box. Remember, the box is accelerating on a horizontal surface, not the vertical surface. So when we calculate the acceleration of the force, we come to Newton's second law. We say force net is equals to mass multiplied by acceleration. And then when we come to find the net force, here we will only accept, or rather use, forces that are making change, or rather that are affecting the motion of this object, which is basically force applied and force friction, which is going to give us mass multiplied by acceleration. And then we have already found out that the net force of the horizontal forces is 15, but we can also continue doing it again. We're going to have 30 and then minus 15, which is equals to mass is going to give us 10, and then we have A. And then here we will end up having 15, which is equal to 10A. And then mathematically, we will end up having 15 all over 10, which is equals to 10A all over 10. 10 divided by 10 is 1. And then here, it is going to give us 1,5, which is equal to acceleration. But remember, we have to write the SI unit of acceleration. Acceleration is going to be equal to 1,5 meters per second per second. This is basically our acceleration of that particular object. And I hope it makes sense. Now, let's find another question to use the ones of at an angle. Question 2. Hinza is pulling I'll use a box, and also a box of 50 kg at an angle of let's say 30 degrees with the force of, let's use 30 newtons, and the box experiences a frictional force of 5 newtons. Yes. And then first question also will be question 2.1. Draw a free body diagram. And then again, let me just say 4 again. And then question 2.2, what can we find? Calculate normal force. Two point three, calculate acceleration. Cool. Now let's check solutions. I'll write SOL, solve for solutions. So now let's come with 2.1. Free body diagram. We have 4 marks. Our beautiful dot. Right? Or rather, sorry, I did not draw the structure. And then I did not tell you which direction. The box is going upward. Pulling a box of 50 at an angle of 30 degrees. Let me just say upwards. Upwards. Sharp. So now the box will be (30°). Force applied is 80 newtons, and then Fk is going to give us 5 newtons. And then we'll come to our solution. 2.1, free body diagram. We start with a beautiful dot here. And then let's start with things that we know. 3 beautiful forces that we know. We have Fk, we have normal and weight, and then we have an angle, or rather force at an angle, force applied, normal force, weight, and then Fk. Voila, our 4 marks. Beautiful. Now, I would like us to also draw the free body diagram of Max. It's going to be so much convenient to us, of us. Remember, how is it going to be? We break these components. Force Y is going to go up. We have normal force. We have force Y. We have Fx. We have Fk. We have Fg. Force applied. Fy. Normal force. Fk. And then weight. Now that we have that, I'd like also to list the data. My board is so small, tiny. And then since I have drawn these free body diagrams, I can write my data there on the structure. Erase the structure, and then data, I have mass of 50 kg. I have force applied of 30 newtons. I have Fk of 5 newtons. I have my angle theta of 30 degrees. Basically, that's everything that I've been given here. So I can continue erasing this part. And then the brother Hinza is the one who's pulling this box at an angle going up. I've drawn the free body diagram. I can cancel its question and then check what is the question. Second question asking me. So calculate the normal force. Now let's check something. The object is moving at a horizontal surface. So the object is not accelerating up or down. So now how are we going to find normal force? We start first by remembering Newton's second law. Force net is equals to mass multiplied by acceleration. And like I said, the object is not accelerating vertically. That simply means this is going to be 0. Acceleration is going to be 0. And then when this is 0, this automatically makes this particular part 0. So I can therefore continue by saying is 0. And then how many forces are there on a vertical plane? We have normal, Fy, and weight, which basically we can say the ones that are going up, I'll choose them as positive. I'll be saying normal force plus Fy, and then since weight is going down, I'm going to choose it as negative, minus weight is equal to 0. I automatically remove the MA and put my 0. Now, the question asks me of normal force. So everything that is not normal, I'm removing from the left-hand side, I'm pushing it to the right-hand side. So I'll be having normal force is equal to, check, weight is negative on this side, force Y is positive. So meaning I'm going to start with weight, making it positive, and then Fy making it negative. Let's remember our formulae. Remember, I wrote them there. I want to show you how to use them now. Weight, mg, minus, and then force Y, force applied, multiplied by sine of theta. Cool. What is my mass if I were to use calculations now? My mass is going to be 50 multiplied by 9.8 minus, what is the force applied given? 30. 30 sine of 30 degrees. Cool. Now let us do this. Sorry about that. I had forgotten my calculator somewhere. So now let's check. We have 50 multiplied by 9.8, which is going to give us 490. 490 minus, and then 30 multiplied by sine of 30 degrees, which is going to give us 15. So 490 minus 15, it gives us 475 newtons. So this is our magnitude of normal force. So the reason why I made sure that I ask this question is because a number of people will make a mistake and try to say normal force even in this scenario is equal to weight. But here, no, they are not equal to one another directly, because now we have the third force. I'll call it an intruder for this case, because it has affected our normal way of doing this particular calculations. So basically, this is how we do them. And then this is where the usage of the Fy and Fx come to play. I hope this will make perfect sense. Let's proceed to answer question of 2.3. Question 2.3. Let's check. The object, we are asked to calculate the acceleration. Now let's remember, the object is accelerating on a horizontal plane, or on a surface, meaning we check the forces that are acting on this object, and there are two forces, which is basically, sorry about that, Fx and Fk. We come again and do what? We check force net is equal to mass multiplied by acceleration. We write the total number of forces that are on the surface, or rather the plane in which the object is traveling at, which is the horizontal plane. So we will say Fx, I'll use a plus for now, plus Fk equal to mass multiplied by acceleration. Now, let's remember, what is the formula for Fx? Is force applied cos of theta plus Fk equal to mass multiplied by acceleration. Now, we now have to substitute everything that we are given, and we'll be left with the unknown part. What is our force applied? 30 newtons. Cos of what angle? 30 degrees plus, or rather, if I were to use plus, that simply means I would suggest this Fk is going in the same direction as force applied, but it is not. So I have to say minus, because force K, or rather kinetic frictional force, is going in the opposite direction to the force applied, which is basically in this case Fx. What is the magnitude of the Fk? 5 newtons. So I'm going to write 5. Mass of this object, 50. And then do I have acceleration? No, it is the one that is in question. I'm going to use a rate for acceleration, because it is unknown. Everything else will be in blue until we find the unknown red color. Now let's find here. Cos of 30, I think, is half of 15. Half of 30 is 15. Let's confirm. 30 cos of 30. Okay, my math went through the window. So I'll end up having 25.98. Oh yes, cos of 30 is root 3 over 2. Minus 5 equal to 50, and then unknown a. Now, 25.98 minus 5 is going to give us 20.98 equal to 50a. And then we are basically going to divide both sides by 50. I'm going to erase these questions here. because we are as good as done. And then we have 20.98 all over 50 equal to 50 all over 50 with our A there. And then this will cancel that. And then we need 20.98 divided by 50, which gives me 0.4196. So meaning I can just round it off to 2 decimal places as 0.42 equaling my acceleration. And again, acceleration, I have to write the SI unit. Acceleration is equal to 0.42 meters per second per second. This is basically how I found my beautiful question, acceleration. And then just to recap, we did these two forces because the object is moving on a horizontal surface. And then the mathematics going down is just algebra of mathematics. So now, I would like to suggest that if you have any question, please do not hesitate to write in the comment section and ask of anything that you would want me to explain or rather elaborate. And also, if there is something else that you want me to do, just comment in the comment section and then I'll respond and then do exactly what you would want me to do. And then this will be the end of our session for today. And then I hope to see you again in our next session. Thank you very much and enjoy.